For decades, astronomers hunting for life beyond our solar system kept running into the same maddening wall. They could find rocky planets sitting at exactly the right distance from their star. Not too hot, not too cold. The so-called habitable zone, sometimes nicknamed the Goldilocks zone. What they couldn't do was prove any of those planets actually held onto air. A perfectly placed rock with no atmosphere is still just a dead rock, no more capable of supporting life than the moon is. Telescope after telescope, planet after planet, that same result kept coming back. Good position, no confirmed atmosphere, question unanswered. On July 16, 2026, that wall came down. A Harvard-led team confirmed helium escaping from the upper atmosphere of a rocky planet called LHS 1140b, sitting in its star's habitable zone, 48 light-years away. For the first time ever, scientists had direct evidence that a rocky world outside our solar system had held onto a real atmosphere, one that's apparently survived for more than 3 billion years. Here's the detail almost every headline got wrong. This wasn't the James Webb Space Telescope. The actual detection came from a ground-based telescope in Chile, using a technique so new it hadn't been proven on a planet like this before. The James Webb Space Telescope's part in this story is still ahead of us, not behind us, and that's actually the more interesting part. And here's something that should genuinely surprise you. In the very same system, right next door, there's a second rocky planet that shows no signs of an atmosphere at all. Same star, same neighborhood, completely different fate. By the end of this video, you'll understand exactly why one world kept its air and the other one lost it. If you've ever wondered how scientists could possibly prove a planet 48 light-years away has an atmosphere without ever going there, stick around. The method itself is half the story. And if you want more breakdowns like this, subscribing genuinely helps. Let's start with the planet itself, because the numbers matter here. LHS 1140b orbits a small, cool red dwarf star called LHS 1140, sitting in the constellation Cetus, roughly 48 light-years from Earth. That star itself is about 3 billion years old, and, importantly, inactive, meaning it isn't currently blasting its planets with the kind of violent flares that younger red dwarfs are known for. LHS 1140b itself is what astronomers call a super-Earth, about 1.73 times Earth's radius, 5.6 times Earth's mass, orbiting its star every 24.7 days. It receives about 42% of the sunlight Earth gets, which works out to an equilibrium temperature of around 226 Kelvin. That's roughly minus 47 degrees Celsius, cold by human standards, but within the range where liquid water could plausibly exist under the right atmospheric pressure. It helps to understand why red dwarf stars like this one have become such a major focus for habitable planet hunting in the first place, because it's not an obvious choice. Red dwarfs are the most common stars in the galaxy by far, small, cool, and incredibly long-lived. Some will keep burning for trillions of years, far longer than a star like our Sun. That longevity, and the fact that a habitable zone planet around a small star orbits close enough to produce a strong, easily detectable transit signal, makes them efficient places to search. But there's a well-known catch astronomers call the problem of stellar youth. Young red dwarfs are notoriously violent, capable of unleashing flares and stellar wind, intense enough to strip a nearby planet's atmosphere away entirely within the first billion years of its life, before life would have any real chance to take hold. This is sometimes referred to as the cosmic shoreline problem, the idea that there's a rough boundary of stellar radiation and planetary gravity beyond which a world simply cannot hold on to air, no matter how good its position looks on paper. LHS 1140b's host star being old and calm now is exactly why this particular planet cleared a bar that so many other red dwarf worlds never could. It survived its star's violent youth, and 3 billion years later, it's still got something to lose. The planet isn't new. It was first discovered back in 2017 by Jason Dittman, who at the time was a graduate student, using ground-based transit surveys. When Dittman first spotted it, LHS 1140b was immediately flagged as one of the most promising rocky, habitable zone planets ever found. A genuinely rare combination of size, temperature, and a quiet host star that made it an instant priority target for every major telescope that could observe it. Dittman is still involved in this story. He's a co-author on the new 2026 paper, and he's now an astronomy professor at the University of Florida. Nearly a decade after he first found this planet as a student, the same world he discovered has become one of the most important test cases in the search for habitable worlds. And he's still there, still working on it, watching a decade-long question finally start getting real answers. For years, this planet already had a reputation. Earlier space telescope observations, including James Webb Space Telescope spectroscopy work published in 2024 by two independent research teams, had already ruled out one specific possibility. LHS 1140b almost certainly does not have a thick, hydrogen-dominated atmosphere, the kind you'd see on a mini Neptune. What those studies couldn't determine is whether the planet had any atmosphere at all, or what it might be made of if it did. There were tentative hints of nitrogen, nothing more. The planet sat in this frustrating scientific limbo, too interesting to ignore, too ambiguous to draw conclusions from. That's where Colin Cherubim comes in. Cherubim, a planetary scientist at Harvard, didn't start by pointing a telescope at the sky. He started by building a theoretical model, first principles physics, predicting what should happen to the upper atmosphere of a rocky planet like this one if it actually had air to lose. His model predicted something specific. If LHS 1140b had an atmosphere, it should be actively losing helium from its upper layers, and losing a lot of it. In his own words, describing the process afterward, he said he was just following the numbers, and that the model predicted escaping helium, and plenty of it. A prediction is not a discovery. To actually test it, Cherubim's team needed an instrument sensitive enough to catch a very specific, very faint absorption line from helium in the near-infrared part of the spectrum. They found what they needed at the Magellan Clay Telescope, a 6.5-meter ground-based telescope at Las Campanas Observatory in Chile, which had recently had a new high-resolution spectrometer installed. Cherubim later described the fit as close to perfect for exactly this kind of measurement. It's worth actually explaining how you detect an atmosphere on a planet you will never visit, 48 light-years away, because the method itself sounds almost impossible until you break it down. When LHS 1140b passes directly in front of its star from our point of view, a transit, a tiny fraction of the star's light passes through the very edge of the planet's atmosphere on its way to our telescopes, rather than being blocked entirely. That thin sliver of starlight gets subtly altered. Specific wavelengths get absorbed by whatever gases happen to be sitting in that upper atmosphere. Helium absorbs light strongly at one very particular near-infrared wavelength, close to 1.08 microns. So astronomers don't look at the planet directly at all. They compare how much starlight dims at that one specific helium wavelength versus every other nearby wavelength during the transit. If the planet has no atmosphere, the dimming looks essentially identical across all those wavelengths. It's just a solid disk blocking light uniformly. If there's escaping helium, that one specific wavelength dims measurably more than its neighbors, because helium atoms in the planet's upper atmosphere are absorbing extra starlight at exactly that point in the spectrum. That small, precise extra dip is the entire signal. It's not a picture of the planet. It's a tiny asymmetry in a light curve, repeated and confirmed across multiple observations, years apart, before anyone was willing to call it real. Here's where the story gets genuinely elegant. In 2024, the team caught a rare and useful coincidence. A night when LHS 1140b and a second, smaller, closer-in planet in the same system, LHS 1140c, both happened to transit their star at once. They observed again in 2025. Combined, they gathered about 6.5 hours of near-infrared absorption spectra across both nights. When they analyzed the data, LHS 1140b showed a clear signature of escaping helium in its upper atmosphere. LHS 1140c, its neighbor in the same system, orbiting the same star, showed nothing, no atmosphere at all. Sit with that pairing for a second, because it's the actual heart of this story. Two rocky planets, same star, same general neighborhood, same 3 billion years of history unfolding around them. One kept its atmosphere long enough for helium to still be leaking out of it today. The other, as far as this data shows, has none. That's not a coincidence you can wave away. It's a natural experiment, sitting right there in one solar system, and it's exactly the kind of comparison planetary scientists spend entire careers hoping to find. The honest answer for why they diverged isn't fully settled yet, but the leading factors researchers point to are differences in mass, distance from the star, and how much high-energy radiation each planet caught over billions of years, especially in the star's more active youth. A slightly smaller, slightly closer planet has a harder time holding on to gas against both gravity's limits and a star's radiation stripping it away over time. LHS 1140c specifically orbits closer to the star than LHS 1140b does, on a tighter, faster loop, which matters on two fronts at once. Being closer means catching more of the star's radiation and stellar wind over billions of years, the same slow erosive process that determines whether a planet keeps its air or not. And LHS 1140c is also the smaller of the two planets, meaning weaker gravity holding whatever atmosphere it once had against that erosion. Smaller mass, closer orbit, more radiation exposure. Three factors that all point in the same unfavorable direction at once. It's not a mysterious result. It's close to what you'd predict on paper before ever pointing a telescope at it. What makes it valuable isn't that it's surprising, it's that it's a real, observed confirmation of a prediction, sitting right next to a planet where those same factors broke the other way. There's actually a third planet in this same system, LHS 1140d, found through additional radial velocity measurements after the first two. It hasn't been part of this particular helium study, but its existence is a reminder that this one quiet red dwarf star is hosting an entire small planetary system, not just a single lucky world. And every one of those planets is a separate opportunity to test the same question against a slightly different set of conditions. The result was published in the journal Science on July 16, 2026, with Cherubim as lead author. Co-author David Charbonneau, also at Harvard, has been blunt about why this particular result matters to people outside the field. It connects directly to the biggest question in the search for life, whether we're alone, and this is the first time anyone has actually found a real atmosphere on a rocky planet sitting in another star's habitable zone. Cherubim himself called it a big deal, and specifically framed it as the first time anyone has found an atmosphere on a rocky planet in the habitable zone of another star. That's not headline inflation. Every rocky, potentially Earth-like planet found before this one, and there have been several strong candidates, had either shown no atmosphere at all, or given results too ambiguous to call one way or the other. Now, here's the part I want to be very careful and very honest about, because this is exactly where a lot of coverage overreached. Finding an atmosphere is not the same thing as finding life, and it is not even the same thing as finding water. Helium escaping from a planet's upper atmosphere tells you the planet has retained some kind of gas envelope. It does not tell you what that lower atmosphere is actually made of. It doesn't confirm liquid water. It doesn't confirm oxygen, methane, or any of the specific molecules astrobiologists actually look for as potential signs of biology. Cherubim's own model suggests the deeper atmosphere might contain water vapor and other oxidized molecules like carbon dioxide, but that part is still a hypothesis, not a measurement. Helium alone cannot sustain life, and nobody on this research team is claiming otherwise. You'll likely run into headlines and social posts this week claiming scientists have found aliens, or that a second Earth has been officially confirmed as habitable. Neither of those claims holds up against what was actually published. For life as we understand it to exist, you generally need three things together: an atmosphere, liquid water, and a rocky surface for that water to sit on. This result confirms exactly one of those three, the atmosphere, and even that confirmation comes with an open question about whether it's stable or sporadic. It does not confirm water. It does not confirm surface conditions. It does not confirm biology of any kind, and it was never presented that way by the actual research team. Charbonneau and Cherubim were both explicit in interviews that this is a single, important piece of a much larger puzzle, not a finish line. The gap between "we found an atmosphere" and "we found a habitable world" is exactly the gap the next 4 to 5 years of Webb and Hubble observations are designed to close, one specific molecule at a time. There's also a second, more technical question this data can't yet answer, and the researchers are refreshingly upfront about it. Is LHS 1140b a planet with a stable, steady-state atmosphere, the kind that leaks gas continuously the way Earth's does, or is it closer to a bare rock that occasionally outgasses in bursts, briefly showing helium that then escapes and disappears again? The data so far is more consistent with an ongoing, replenished supply of helium than with a single one-off event, which leans toward the real atmosphere interpretation. But leaning toward an answer is not the same as proving it. This is exactly why the Webb part of this story isn't over. It's just getting started, and this is where the honest version of only the beginning actually lives, instead of some invented sense of dread. LHS 1140b has been selected as one of the target planets under something called the Rocky World's Director's Discretionary Time Program, a joint initiative between the James Webb Space Telescope and the Hubble Space Telescope, specifically built to hunt for atmospheric evidence on rocky planets orbiting small, dim stars. This isn't a vague, someday research direction. It's a formally allocated, prioritized observing program the kind of thing that only happens when a planet has already cleared a high bar of scientific interest. Getting time on the James Webb Space Telescope at all is difficult. Every observing cycle receives far more proposals than the telescope can possibly accommodate, and a dedicated multi-year program built around one specific class of planets signals just how seriously the field is taking this particular question right now. Dittman, the planet's original discoverer and a co-author on this new paper, has been direct about the timeline. He expects the program to be able to prove or disprove a genuine, lasting atmosphere on LHS 1140b within the next 4 to 5 years. The specific thing Webb will be looking for in that window is water vapor, along with other heavier molecules like carbon dioxide that a thin, nitrogen-based atmosphere might carry. If Webb's instruments detect water in that atmosphere, Dittman's own reasoning is that it becomes far more likely this is a stable, persistent atmosphere rather than a bare rock that occasionally burps out gas. If Webb finds nothing, that leans the opposite direction, toward the less exciting but still scientifically valuable answer that LHS 1140b periodically outgasses helium without holding a true, breathable envelope underneath it. Either answer moves the field forward. That's what makes this a genuinely open, honest scientific question rather than a headline waiting to be confirmed. 4 to 5 years. That's the real, dated, honest timeline behind the second Earth headlines you're going to see attached to this story. Not a countdown to some dramatic revelation next month. A genuine multi-year observational campaign, using 2 of the most powerful telescopes humanity has ever built, aimed at a single, specific question: is there water on this world or not? It's worth pausing on why this particular technique matters beyond just this one planet. Cherubim didn't get lucky. He built a model, made a specific, falsifiable prediction, and then went and tested it with an instrument built for exactly that purpose. And the model held up. That's a template now, not a one-time result. The same approach can be pointed at other rocky, habitable zone candidates orbiting other small stars, and critically, this particular detection method doesn't require scarce, oversubscribed Webb observing time at all. It's ground-based. That matters practically, because Webb time is one of the most competitive resources in modern astronomy, split among thousands of proposals every year. A validated ground-based method for flagging which rocky planets are worth Webb's limited attention could meaningfully speed up the entire search. To understand how significant that actually is, it helps to know how many previous candidates fell short, and how each one failed differently. TRAPPIST-1, a system of 7 roughly Earth-sized rocky planets orbiting an ultra-cool dwarf star just under 40 light-years away, was one of the most hyped discoveries of the last decade, with 3 of its planets sitting in the star's habitable zone. Webb spent significant observing time on the system, specifically to check for atmospheres. The results were sobering. Webb observations eventually ruled out any Earth-like thick atmosphere on TRAPPIST-1d, and separate measurements of TRAPPIST-1b and c found those inner planets were most likely bare rock, their atmospheres almost certainly stripped away by the star long ago. TRAPPIST-1e, generally considered the single most Earth-like planet in that system, has remained frustratingly inconclusive even after repeated observation, neither confirmed to have an atmosphere nor ruled out. K2-18b tells a different kind of cautionary tale. It's not even a rocky planet in the same category as LHS 1140b. It's a larger sub-Neptune, potentially a water-rich world, and in 2023, a research team reported a possible detection of dimethyl sulfide in its atmosphere, a gas that on Earth is produced almost exclusively by marine phytoplankton. For a brief period, this was treated in some coverage as tentative evidence of biology on another world. A more thorough, NASA-led reanalysis published in 2025 walked that back significantly, finding the original signal too weak to stand behind with real confidence, and pointing out that the same molecule can form through entirely non-biological chemical processes anyway. It's a useful case study in exactly the trap this LHS 1140b story could fall into if people aren't careful. An exciting, technically real signal, stretched by enthusiasm and headlines into a claim the data never actually supported. Against that backdrop, years of near misses, stripped atmospheres, and walked-back biosignature claims, an actual, confirmed atmosphere on a genuinely rocky, habitable zone world, replicated across 2 separate observing years, is a real and rare milestone. It's just not the milestone some headlines are claiming it is. So where does that leave LHS 1140b, honestly, today? It's a rocky planet, roughly Earth-sized, sitting in its star's habitable zone, orbiting a quiet, inactive star, old enough that its violent youth is long behind it. It has confirmed helium escaping from its upper atmosphere, which means it has held on to some form of atmosphere for a very long time, possibly billions of years. Its neighbor in the same system appears to have lost that fight entirely, giving researchers a rare natural comparison to study. And whether that atmosphere contains water, whether it's stable rather than sporadic, and whether any of it points toward genuinely habitable conditions, is a question two of humanity's best telescopes are now going to spend the next several years actually trying to answer, on the record, with a specific and dated observing program already assigned to do it. It's also worth stepping back and asking what this means beyond just one planet, because that's arguably the bigger story hiding underneath the LHS 1140b headlines. Until this result, nobody actually knew whether it was even physically possible for a small, rocky world orbiting a red dwarf to hold on to an atmosphere for billions of years. That was a genuinely open question, not a settled assumption. Red dwarfs make up roughly 3 out of every 4 stars in the galaxy. If rocky planets around them simply cannot keep their air, that would quietly rule out the vast majority of stars in the Milky Way as places to even look for habitable worlds. This result doesn't prove the opposite is universally true, but it proves the door isn't closed. At least one rocky planet, around at least one red dwarf, made it through billions of years with its atmosphere intact. That changes the odds, even if only slightly, for every other similar system astronomers haven't looked at yet. If you want one sentence to take away from this, for the first time we found a rocky planet in another star's habitable zone that actually kept its air, and now we get to find out, with real data instead of speculation, what that air is actually made of, and what that means for every other quiet red dwarf star out there we haven't checked yet. We'll keep tracking this one specifically, because unlike a lot of space stories, this one has an actual scheduled deadline for real answers. If you want to know the moment Webb's water data comes back, subscribe so you don't miss it. And if this helped you understand a headline you'd already seen but never quite had explained properly, send it to someone who'd find it useful too. Stay curious. I'll see you in the next one.